In the previous video, we introduced the notion of the Fourier series and discussed how to compute Fourier coefficients, as well as the theorem that explains when the series converges to its function. And in this final video of the course, we'll return to studying the heat equation using the Fourier analysis that we have developed on the previous video. Let's recall the heat equation. So in one special variable x, it looks like this: the time derivative of temperature U as a function of x and t, the partial time derivative is equal to heat transmission coefficient beta times dt over dx squared, the second partial derivative of temperature with respect to x. And we saw that the solutions are given by three different formulae, depending on the sign of the eigenvalue lambda of the second derivative operator. So it's either the exponential functions of x and t, linear function in x, or the oscillating trigonometric functions in x and exponentials in t. So previously we talked, so we considered a wire of length L, whose endpoints were kept at temperature 0. So we had boundary conditions u of 0t is equal to u of L of t is equal to 0. And of our above equations, the only ones which takes the form are the following. So it's it must be a sine function, right? Because it ranges at 0 at the next nodal point, multiplied by the time exponential. So, and that requires that the square root of negative lambda over beta is an integer multiplied by pi divided by L. And the general solution could be presented as the following series. And we talked about initial temperature, initial value problem in the context of Fourier with the heat equation. So consider the initial temperature distribution at time t equals 0. And our job was to express this function as the expansion in sines. So it was a combination Cn sine n pi over Lx. So in other words, to find, we needed to find the coefficients Cn making the above formula true. So because the solution will be given by this infinite series, so because since the solution will be given by the series in sine functions, it's what we need to do is to first rewrite. We need to Fourier expand. We need to write down the initial value function t of x u of x0 as the Fourier series with some coefficients, because then it will be easier to compare those coefficients with the form in which the solution is written. So this expression is exactly the Fourier transform, is the Fourier expansion. So two differences from the previous video are that the function is only defined on the interval from 0 to L. And second, that we want to expand it only in sines rather than in sines and cosines. Because in general, Fourier expansion gives you sines and cosines, but however, as we saw in two different cases, sometimes only sines are present and sometimes only cosines are present, provided that the certain parity conditions are satisfied. So here's the recap of the Fourier coefficients. So we have a constant term, the cosine series and the sine series, if the function is defined from negative L to L. So to observe those differences between this treatment of Fourier series we had and what we need here, we'll continue the function, we'll extend it from 0L to negative LL by simply sort of extending it such that the function is odd. So f at negative x is negative f of x. So that will make sure that only sines will remain. So sines will only remain and the cosines will disappear because of parity. So it's a certain choice, it's a choice that we made, but it's it's a tool which will help us to calculate the answer. So in interpreting the answer, we just ignore the value of the function on negative L to 0, right? Because it was our mirroring trick. Let's do the example. I take a wire of length L and diffusivity beta, or heat transmission coefficient beta, in which the initial temperature is described by a function. So it looks like x from x goes to from 0 to L half, and L minus x on the second half of the segment. So if you draw it, it would look like this. So if this is L, this is 0, it would be a wedge like that, right? Yeah. So this is U of x. Let us determine the temperature in the wire as a function of time. So first, we should expand out this function, U of x, into its sine Fourier series. Well, we know this. We need to compute those coefficients b sub n, integrating out those f times sine n pi x over L. So of course, we break the integral into two, from 0 to L half and from L half to L, because the function is given piecewise, right? So after change of variable, we get L over n pi squared factor in front, and then integral from 0 to little n pi over 2, u sine u du, and this integral of n pi minus u sine u du. So we need to apply the so after integrating by parts, we get this formula. So integrating u sine u du is sine u minus u cosine u, and then we just substitute it as in the fundamental theorem of calculus. There's a standard computation, which I hope you can do by yourself. Yeah, so there's that formula. There's several substitutions that we need to do carefully. And the answer will be given by 4L divided by n pi squared times sine n pi over 2. So please pause here, pause the video here, and then do the calculation yourself. So the Fourier expansion of the original function u of x is therefore given by this formula. So we have sine x, sine 3x, sine 5x, sine 7x, 4 divided by L over 2 pi. And finally, we can write the initial condition as such. So, and then we see that if you substitute this into the full solution of the heat equation, we'll also need to combine it with those time exponents, right? So we'll have e to the negative beta pi over L squared t, then e to the negative 3 pi over L squared t, and so on and so forth. So this is how the temperature will go in time. So if you try even draw the evolution, so initially temperature would look like this, and then it will start to kind of even out, right? So it will kind of go like that. So another sort of boundary condition we might impose is instead of fixing the initial and final temperatures to be 0, so that the wire is insulated, we can impose that derivatives vanish identically at 0 and L. So this is so-called Neumann boundary conditions as opposed to Dirichlet. So let's revisit our possible solutions. So the 3 cases, right, depending on the sign of lambda. And you can try yourself to see which of them satisfy this given boundary conditions. So, and yet maybe a third scenario where you could consider to ask that at L0 and L, the temperature is fixed to some given constants, U1 and U2, possibly non-zero. And then again, you can ask yourself what will be the corresponding boundary conditions. So perhaps in this case, you need to invoke some of the exponentials here. So not only sines and cosines, but also exponentials and linear functions. So I'll leave it to you as an exercise.